How did I do this well despite having stupid moments that entire time?
Your program gave the right output, and so that was a good thing. That automatically got you a bunch of points, and all of your code looked like it would work if I had tested that area. So the assumption is that if you got enough of the jumps right to make my program give the right output, all of your other jumps, if they looked exactly the same with minor differences, they were right as well. There were some questions on the homework that's due this week. The homework is due Thursday at 11:59 p.m. Or more realistically, when I wake up when I wake up on Friday morning, which it doesn't give you that much leeway. That'll be about 3 a.m. I get on a plane at 6 a.m. It's not my choice. It's just scheduling. There is nothing posted on the website about Homework 7. Homework 7 is 2 sentences. Implement heap sort and selection sort. Build a large array and prove that heap sort is quicker than selection sort. That's it. I'm not going to write an entire PDF just with those 2 sentences. This really shouldn't be that difficult in terms of making sure that you hit a whole bunch of points. The reason that all of the other assignments were big long PDFs was because there were several parts. Make sure you implement this method, make sure you implement this method, make sure you implement this method. So I guess to go into a little bit more detail, you should have a method called heap sort and a method called selection sort. Both of them should somehow operate on an array and eventually sort it, doing the appropriate things. You should save the time, create your large array, save the current time, execute one of the methods, save the current time after executing the method, and show how long it took to execute that method. Do the same thing for the other one on exactly the same array. So if your sorting functions, if your sorting methods do an in-place sort, make sure you make a copy of the original array so that you can pass one copy of the original array to heap sort, another copy of the original array to selection sort. That way you don't end up passing a sorted array to whichever one you call second, because that'll skew the results. Does that make sense? Cool. And if you have until 11:59 on Thursday to hand it in, but if you get it in early, I will grade it early, post the grade, and that means I won't have to do as much on Friday in the airport. I'll post it on Blackboard.
Maybe get some extra points if you get it early, even if it's worth to do on Friday.
I do not believe in extra credit. People have tried to get extra credit out of me before. It hasn't worked. My reasoning for that is that I can't figure out a good way, a way to give extra credit and still have it be fair to everybody. So I just avoid the problem and don't give out extra credit. There are no extra credit opportunities in any of my classes. So. Right. So we have an exam on Thursday. Let's talk about the exam. Let's hope it doesn't open. Yeah, good. Okay. There are exactly the same number of questions on the final as there were on the midterm. That's just how it worked out. So there are 13 questions. It is worth 200 points. It is divided into 4 sections. Part 1 is on searching and sorting. There are 2 questions on searching. And there are 2 questions on sorting. The 2 questions on searching have to do with the 2 types of searching that we talked about, and kind of comparing them. So, when is one better, when is another better, that sort of thing. the two questions on sorting have to do with the two general classes of sorting algorithms that we talked about. We talked about, and these are the ones in the book. So bubble sort is not on it. But we talked about 6 different sorting algorithms. Bubble sort, selection sort, insertion sort, those are all n-squared algorithms. We talked about merge sort, quick sort, and heap sort. And those are the faster algorithms. So there are only, in this section, there are only 3 that are talked about. The other 2 sorting algorithms that are in the book are talked about in other places in the exam, I think. No, just one of them. The second part is about trees. And since it's a data structure, the first question is very similar to the first question for each of the data structures on the midterm. Basically, describe what it is and how it works. Make sure you hit both of those points, what it looks like and how it works. On the midterm, some people miss one or the other of those things. So both of those are important to get full credit for that question. Question 6 has to do with specifically what makes a tree a binary search tree. And question 7 has to do with taking a tree and making it basically making a tree map. So instead of having just values in a tree, having key value pairs in a tree. So you can create something like a lookup table. Part 3 is heaps. And question number 1, since heaps are like trees, it is not like the first question, not question number 1. Question 8. The first question about heaps is not like the first question about trees or the first question about any other data structure, because if you know what a tree looks like, you know what a heap looks like. It's more like the second question having to do with trees, which is what makes a heap special? What makes a tree a heap, basically? I did put that question on here. On the 1150 exam, one of the questions is, what is recursion? That is basically question 9, with a little bit extra. Specifically, what is recursion when we're talking about heaps? And then question 10 is talk about heap sort. So after doing this homework assignment, you should know how heap sort works. I recommend doing that part before the exam. It'll be good studying, good preparation. And then part 4 is about graphs, which is what we're going to talk about today. Hopefully I won't get too overexcited and miss anything important. The first question, since the graph is a new data structure, it is the standard question. What does a graph look like? How does it act? Then the other 2 questions for graphs, that's 12 and 13, are one of the things that we're going to talk about today is how graphs are kind of the most general data structure. And so question 12 talks about how can you implement some of the other data structures in terms of a graph? How are they similar? And question 13, you get some freedom with. I'll actually tell you the question right now so you can be thinking about it for Thursday. It is, describe one real-world situation that can be modeled using a graph. What is modeled by each of the nodes / vertices and edges? and we'll talk about what nodes and vertices and edges are today. And hopefully I'll give several examples as to real-world examples that you can use graphs. It would be awesome, though you won't get more points, if you pick one that I don't use as an example. Because graphs can be used, there are so many different ways that graphs can be used. You're welcome to pick one that I use. You're welcome to pick one that you're walking around and all of a sudden you look at something and all you see are graphs. That's cool. That would be awesome. That's what I do. If you pick one that I use as an example, make sure you understand why you can use a graph to simulate this problem. Don't just say this can be used, a graph can be used to simulate this problem because Brian said so. That's not a good answer. That won't get you very many points. That question is only worth 10 points, so that won't get you very many points at all. The exam, not the book, not the question. The exam is open book, closed notes. So you can't use any previous programming assignments, can't use any notes that you've taken in the class. Just the book. You can use the book that you have, even though it's not the book that we were using. It'll certainly help as reference material. I don't think there's much in the way of you can copy out of the book. You'll probably run out of time if you try doing that. And the format of the time format of the exam will be the same as for the midterm. The first half of the class is exam taking time. The second half of the class is talking about the exam. If it looks like the first half of the class is not going to be enough time to finish the exam, I'll make a decision at 2:55, I think. Yeah, 2:55, and decide if we need 15 more minutes, 10 more minutes, an extra half hour, or something like that. It won't take the entire second half of the class to talk about the exam. It took us, 20 minutes to talk about the midterm? I expect it'll take approximately that amount of time to talk about the final. Of course, if it gets too long, then I will cut you off, and if you don't finish, can't really do anything about that. This exam I don't expect this to be a long exam. You don't have to write an essay for each question. A few sentences will do, as long as you answer all parts of the question. If you can answer all parts of the question in a single sentence, that's great. In a sense, the essence of technical writing is saying the most you possibly can in the fewest number of words. That still makes a good sentence. If it's unreadable, it doesn't matter what you say. So shoot for being concise while maintaining clarity. And that makes it easy to grade too, because little secret in grading short answer tests, teachers can usually figure out what you're saying after reading the first 6 to 10 words of your response. So if you start off those 6 to 10 words going in some completely different direction, they don't need to read any further. Even if you've written an entire paragraph, you can skip down to the end, make sure that you didn't sneak the right answer in somewhere and just mark it wrong. If those first few words are going in the right direction, as long as nothing is blatantly wrong in the rest of the paragraph, you can just mark it right and move on to the next question. So those first few words are key. If you write a very long paragraph, the likelihood is that I'm not going to read it all the way through. I'm going to skim for keywords. And 99% of the time, I figure out if you got the right answer or didn't get the right answer fairly quickly. No, if you do that, it's pretty obvious when you sneak in keywords that don't fit in with the rest of the paragraph. That said, if you don't know the answer to something, do not under any circumstances leave the question blank. The worst thing you could do on a short answer test is leave a question blank. You're guaranteeing that you won't get points for that question. If you want to try Dion's strategy and hope that you can trip me up, go right ahead. If you demonstrate that you understand what the question is asking, that is better than leaving the question blank. And of course, if you can start heading in the right direction, like, I don't know exactly what you're looking for here, but given the question that you've asked, this is what comes to mind. That will get you some points. The way I try to write my tests, especially when it comes to short answer questions, is that just by sitting in class and paying attention, keyword paying attention, hopefully reading the question should elicit some memory of something that you can then write down on the paper and get some points for. But the questions will be just hard enough that if you only did that, it might be difficult to pass. So understand the material and you'll definitely pass. You'll definitely pass well. Pay attention and you might scrape by. Questions on, yeah.
So are there going to be like because in your last test you had some questions that involve like pseudocode? Do you have some
There are no questions on pseudocode. There are questions that you could answer with some pseudocode, but there are no questions that specifically require pseudocode. Any other questions on the content? Yes. Part 3 is heaps. So part 1 is searching and sorting. Part 2 is trees. Part 3 is heaps, and part 4 is graphs. So basically the same format as the midterm. 3 sections on the 3 major data structures, and then 1 section on general kind of cool concepts. There's nothing on generics. That's midterm stuff. Like the syllabus says, there's nothing on the final will specifically be about stuff that was on the midterm. But you might need to understand some stuff that was on the midterm in order to understand the stuff that's on the final. Any other questions? Cool. All right, so let's talk about graphs. Before we dive into the chapter, anyone have any idea what a graph is? Whether you read the chapter or not. This question still applies. Anyone? Okay. Cool. Right. So, at its, generally, so, as you get kind of higher up in what data structures can do, you get more capability and fewer rules. So trees had very specific rules. Binary trees are a subset of trees and had even more specific rules. Heaps, same thing. Graphs are kind of, and when we were talking about trees, I mentioned that linked lists were kind of an extra specific case of trees. Some special rules apply. Graphs are kind of a step up. So every tree is a graph. Not every graph is a tree. But like that sentence says, graphs consist of, what did it say, nodes? Nodes and links between the nodes. Usually they're called vertices, that's the plural of vertex, and edges. I threw all the markers away, so no drawing in the board today. I got tired of them not working yesterday and just threw them out. Okay, so a graph, in the general case, has a set of vertices and a set of edges. And that's usually denoted as, it looks like an ordered pair. It's in parentheses V, comma E. V is the set of vertices, E is the set of edges. And the vertices are nodes. Nothing real interesting there. Kind of a dot. With trees, they stored some value. With graphs, they're usually connected to some value as well. But they don't really have to be, depending on the application. Edges are simply ordered pairs of vertices. So an edge is something connecting this vertex over here, this node, to this node over here. And there's an edge there. That's it. So graphs, as a data structure, are very simple. There's really not much to them. The complexities come in the types of graphs. So the most general form of graph is an undirected graph. Basically, no restraints on what nodes you have, what edges you have, what edges connect what nodes, how they're connected. If you were traversing the graph, there's no restriction on which direction you can traverse an edge. If you have two vertices and an edge between them, you can go from this vertex to that vertex, or you can go from this vertex to that vertex. No restriction whatsoever. You can have directed graphs, where not only does an edge connect two vertices, it also has a direction. So it goes from this vertex to this vertex. And usually that's denoted by saying that the order in which the vertices are listed in the definition of the edge implies some direction. So if I have vertex 0 pointing to vertex 1, that means that that edge only has the direction from vertex 0 to vertex 1. If I'm traversing the graph, I can't go from vertex 1 to vertex 0, at least not along that edge. Graphs can also be acyclic, which means there are no cycles on them. You can't start at one node, take one edge, and through any other path get back to that same node. And you can have those in either undirected or directed graphs. In undirected graphs, you can travel along an edge in any direction. So if you have any sort of connection, I keep trying to go for the markers that aren't there. If you have any sort of connection that ends up looking like a circle, you have a cycle and it's not acyclic. In a directed graph, you can have the only way you can have a cycle is if you follow an edge in the proper direction, follow another edge in the proper direction, and eventually get back to the starting node. If you have one starting node that has two edges going in different directions, and then somewhere along the line they join back up and have a node in common, that is not a cycle. Because you can't get back to the starting node. Even though there is, when you draw the graph out, there is some closed area, if you will. If you were to color between the edges, there is one region that you wouldn't be able to get out from. So a directed acyclic graph sounds a lot like a tree, but it's not quite a tree. Because in a directed acyclic graph, you can still have two paths that lead out from one node and eventually join up again. That doesn't violate either the directed nature of this directed acyclic graph, sometimes called a DAG because it's abbreviated, directed acyclic graph. So it doesn't violate the directedness. It doesn't violate the acyclic nature of it. Obviously, it's a graph. But it's not a tree because the definition of a tree in terms of graphs is that there is one starting node where there are no A tree is a directed acyclic graph that has a root node, something that we can call a root. And that root node has no edges entering it, going to it, only edges leaving it. So there are only edges that start at the root node and go somewhere else. So in our binary tree, we have the root and it goes to potentially two other child nodes. We have 3 nodes and 2 edges. The second thing is that any node the nodes other than the root node only have one edge entering them. They can have many nodes, many edges leaving them, but they only have one edge entering them. Otherwise, we would have this case where you'd start at the root node, follow 2 paths, and get to the same node. That can't be. Basically, that means that there is one unique path from the root node to any other node in the tree in order for it to be a tree. Also, a kind of a corollary from that, if a tree has n nodes in it, it has n minus 1 edges. And if I could draw, I could prove that to you. But in the example where you have 3 nodes, a root and 2 children, you have 3 nodes and only 2 edges. Add 2 more nodes, you add 2 more edges, you have 5 nodes and 4 edges. So you can extend that as far as you want, but that's always the case. For n nodes, you have n minus 1 edges. And that's an easy starting point, at least, to determine if a graph is a tree. If those numbers don't match up, the graph that you're dealing with is not a tree. So far, we've been talking about something called connected graphs. This is where there is a path from, if you ignore direction, there is a path from any node to any other node. If you enforce direction, there is a node in the graph such that every other node is reachable from that node. Even that's not true in a connected graph. There is a connection. If you have a cluster of nodes, they are connected to every other cluster of nodes in some way. Basically, that means you can't have some nodes that are connected over here and then some nodes that are connected over here. They are both individually connected graphs, but the thing as a whole is not a connected graph. It is still a graph, it is just not a connected graph. Right, so places where graphs are useful. You can talk about the highway network between cities in terms of graphs. Each city is a node, and each highway is an edge. Another term for graphs is network, and boy, that just opens up a lot of possibilities that you can use as examples for graphs, or situations that you can use graphs to model. The internet, for instance. A network within an organization is another instance. Hopefully it's a connected graph. If you're in the DoD space, you might get a non-connected graph, where you might have some net over here that's not connected to anything else. The brain. Networks and graphs are used to model the brain sometimes. And there are various different levels where you can model that. Either if you look at neurons as individual nodes and the connections between them as the edges, that works. If you have different centers within the brain and treat them as nodes and the pathways between them as edges, that works as well. And there's nothing preventing, in a graph, edges can have weights, they can have speeds, they can have other attributes that might determine how the graph operates in your particular. I'm just going to give up speaking a minute. I don't know, what was I saying? Depending on your specific situation, you might have other data attached to the edge and attached to a node. So in the case of a network graph, you might have, your nodes might be routers and your edges might be the links between them. That's probably the simplest example. Routers usually have some memory. Quick tutorial of the internet. When you send a message from one computer to another computer, first it goes through a shredder. No, it goes through a dicer. When I'm thinking about this, I think about chopping onions. You set the onion on a cutting board and take the knife and chop sequentially, and you get lots of onion slices. So if you take your message and think of it as it's now a bunch of onion slices, and one by one they get sent to the next node, which is not the final destination. There are a bunch of hops between the starting point and the ending point. One by one, these onion slices get sent off to the first node. That first node then is responsible for sending it to the next node. The next node is responsible for sending it ... eventually to the endpoint where it reassembles the onion. So each router has some certain number of onion slices that it can hold. Let's say 2. Each wire has some speed. Each pathway has some speed. Usually referred to in terms of latency, so the opposite of speed. How long do I have to wait before I can send the next onion slice? Then routers have that memory. How many onion slices can I keep in memory at a time? So add all that together, you get some overall latency. And you can use graph theory, network theory, to determine, first of all, what pathway it's going to take and what the overall latency is. And there's actually an example in the book. Anyone know who Edgar Dijkstra is? Cool. He won the Turing Award. Smart guy. This book calls it the shortest distance algorithm. I wasn't even really reading the book. I was skimming through it, saw this, and said, ooh, Dijkstra's algorithm, and then saw the caption, and it was shortest distance algorithm. It is Dijkstra's algorithm. And that section is definitely worth reading. Probably one of the coolest things in network theory. And the idea of Dijkstra's algorithm is it determines the shortest distance, or it is now used as the basis for many network routing protocols to determine the most efficient route to get from point A to point B. And the idea is start at point A, figure out what we know. We know it takes 4 milliseconds to go to that node and 8 milliseconds to go to that node. Okay, now get the information from those nodes about how long it takes to get to their next nodes. Now I know how long it takes for me to get to the nodes that those nodes know about in the shortest amount of time. It might be going through this node, it might be going through that node. And the example on pages 761 through the book spends several pages on it. 766. Well, no, it keeps going. Basically through the end of the chapter. 760 to 771. kind of overshadows the other algorithms that it mentions, which are determining whether a path exists and determining what the shortest path is using graphs with weighted edges. So not only does an edge is an edge an edge, so you can count edges and determine the shortest path based on how many edges there are between node 1 and node 724. You can also give each edge a weight, and that's something like latency. So I might be able to get to node 724 by going through this router or going through this router, but this router and the links that it's connected to are a lot quicker, so a lot lower latency. So the shortest path is through that router, even though both paths are directly connected to node 724 as well as directly connected to me. So there are two edges between me and that node, regardless of which direction I go, but this route is faster. So that's the shortest path. Let's see. Other stuff. Graph traversals. So just like we can traverse a tree, we can also traverse a graph. It gets trickier when we have directed graphs because depending on what node we start at, we may or may not be able to, all the other nodes may or may not be reachable, which means from a given node, we can get to every other node. Or if a node is reachable from another node, it means that that node, there is a path to that node from the starting node. With undirected graphs, we can do things called depth first search and breadth first search. And depth first search starts by going as far as it possibly can and then backtracking. Breadth first search starts by checking out all the children first. So now is when I really wish I could draw. The basic idea behind depth first search is pick a starting node. That starting node has connections to some subset of nodes, or some set of nodes. Pick one. In general, we pick the left one, whatever left means in our particular context. Go to that node. Do the same thing. And do that until we reach, either can't go any further, that means we get to a node where the only connection is the one we just took, or it loops back to a node we've already seen. Either way, that ends, it's basically recursion again. That ends that branch of recursion. We backtrack to the next node up, or the next node closer, and go to its second from the left child, and do the same thing. Go down that branch and keep going down the left child. Eventually, we exhaust that possibility and backtrack. Do the same thing with the next node, and keep going. And eventually, we will have enumerated all of the nodes. While we're doing this, we should keep a record of what nodes we've seen. Eventually, we will have enumerated all nodes, and if it's a search, we can short circuit when we find the thing we're looking for. Depth first, no, that was depth first search. Breadth first search does kind of the opposite direction. Instead of picking a child and keeping going down that branch until we exhaust all possibilities, breadth first search looks at all the children, says, nope, I haven't found it yet. Then picks one child, does the same thing with that child. Then goes to the next child of the starting node, does the same thing, goes to the next child of the starting node. And this breadth first search, you can use a queue for this, or something like that. Depth first search is really good with recursion, because it's basically the same thing we've done with trees. With breadth first search, which is, I want to say it's more efficient. I don't know if it's more efficient. I don't remember. It's really cool though, because you get to use additional data structures. So initialize a queue with the root node, or we don't have a root node. Initialize a queue with the starting node. Add to that queue all of its children, assuming we don't find what we're looking for in the children. Then we're done dealing with the starting node. We can pop that off the queue. Pop the next thing off the queue. Push all of its children onto the queue. And basically we end up with, if we start out with some, let's pretend we're starting out with a tree. It makes visualizing easier. We start with the root node, pop that onto a queue. Then that next level, pop that onto the queue. Push that onto the queue. It's pushed onto the queue. The root node gets popped off the queue. We're done with it. Then that next level gets pushed onto the queue. Then the next level gets pushed onto the queue. And we actually end up with something that looks like that example very early on when we started talking about trees, where they had algorithms in an array, and we're talking about how that can be interpreted as a tree. We basically have that, except we're popping a bunch of things off as well. So now we get into the big problem solving game. We want to represent a graph in Java. So we know what a graph looks like. We know what a graph should do. We know how a graph should act. But how do we represent it in Java? If you read the chapter, you know that there are two ways. If you haven't read the chapter, you might be able to figure out that there are two ways. Any ideas? Dion, what's one way? If you were approaching this problem, how would you make a data structure to represent a graph? So here's maybe a slightly easier question. If you were going to create a graph data structure in Java, what questions would you ask to solve that problem? No, even higher level than that. We haven't really talked about how we interact with the graph data structure quite yet. But we're talking about how we would store all the data that is necessary for a graph. Right. So we have so we have nodes and edges. Nodes is a set of things, and edges are a set of things. So I guess there are actually three ways we can store it. Three ways that I can think of it. The book mentions two, but we'll expand that to three. So if you have nodes and edges, how would you store nodes and edges in Java? You have an idea? So that's one approach. Not exactly a linked list, but that idea of a node is an object, and it has some collection of pointers or references to other nodes, right? So that's one of the ways that the book mentions, and that is efficient when you have a potentially large number of nodes and a potentially small number of edges. So this graph is very sparse. The word is sparse, meaning there aren't a lot of edges connecting the nodes. So a tree is very sparse. We said that with a tree, the number of edges grows with the number of nodes, directly in proportion. In the general case of the graph, if we have n nodes, we could have potentially n squared minus n. If we have two nodes, the most edges that we can have is 1. If we have 3 nodes, the most edges that we can have is 3. So it depends on whether it's directed or undirected. If it's directed, for each pair of nodes, we have 2 possibilities, either going this way or going this way, which basically means it's n squared on the number of nodes. Well, n squared minus n, because most graphs don't have edges linking back to themselves. Though they can. The book calls that a loop. And that's one rule you can impose on your graphs, whether or not loops are allowed. With an undirected graph, between every pair of nodes, there's only one possible edge. Which means that it's basically half of n squared. Which is still n squared. So if you have a potentially large number of edges, that method does not work as well. It's not as efficient because you end up having lots of references to all these different nodes. What's another way that we might be able to store a graph in terms of Java? So that's the very tree-like method. The other methods, the other techniques, center very much on the idea that the definition of a graph is a set of vertices and a set of edges. In fact, both of them treat the set of vertices as it's an array of things called vertex. Whatever a vertex object looks like, it's an array of vertices. The question is, how are we representing these edges? If we're not representing them in terms of references that are part of the vertex object, we have to store them somehow. Jack, do you have an idea? Okay. How about you, Clark? So one approach, and this is the one that the book doesn't talk about, is that we can have an array of edge objects, whatever an edge object is. An edge object should have either references to 2 vertices or just indexes to 2 vertices, the index into the vertex array. That says this edge connects these 2 vertices. It's fairly efficient for storage, but if you're going to do any sort of graph traversal, it's not very efficient because you have to look through this list of edges in order to find the edges that correspond to the vertex you're starting at. Which, there's really no good way to perform binary search or any sort of sorting on edges. Because you have no way of knowing which vertex you're starting from. Unless there's only one direction that in this entire graph you can go, which is not likely the case. So it would be nice if there were some way we could directly index if there is an edge connecting this vertex to any other vertices, it is going to be right here. And there is a way. It's a 2-dimensional array. Sometimes called an edge matrix. It's basically a square matrix labeled, each row corresponds to the starting vertex, and each column corresponds to the destination vertex, or reverse, doesn't matter, as long as you're consistent. And if you, it can be a Boolean matrix. If there is a 1 there, if there is a true there, there is a true there, that means there's an edge connecting vertex 1 to vertex 3, or something like that. If it's a non-directed graph, you really only need half of that. Because a connection in one direction implies a connection in the other direction. If it's directed, then if you're looking to see whether there's an edge connecting vertex 5 to vertex 6, you scan down the first dimension of the array to index 5. Let's say our vertices are also indexed at 0, starting at 0. So vertex 5, go down in the edge matrix to subarray 5, scan across to slot 6. If that is true, then there is an edge connecting verse 5. Vertex 5 to vertex 6. Ooh! I just found another case where graphs can be useful. So, who's familiar with the Bible? I have to tread carefully here because I'm not supposed to talk about religion and culture. However, the Bible, as we read it, if we read it, is in English. It was not originally written in English. It was originally written in Hebrew, Greek, and Aramaic. Hebrew, Aramaic, and Greek in order. So let's ignore the Old Testament for the time being. Let's talk about the New Testament. Entirely written in Greek. There is a finite set of Greek words that were used to write the New Testament. Each one of those Greek words can be, we could call that a vertex. And every Greek word that follows that word, anywhere in the New Testament, can be treated as another vertex with an edge between it, a directed edge. And by so doing, we can construct a graph of the New Testament. And that would be really cool. And that's actually, this falls into something called natural language processing or text processing. And people do that not just on the Bible, but also on English words. In English, it gets pretty dicey because automating that, there are a lot of different ways to say the exact same word, or spell the exact same word, or use the exact same word and put different endings on it with different surrounding words. Greek is much more well-behaved. A single root word with slightly different endings indicates the difference between I walked, he walked, she walked. No. He, she, and it walked is the same. You walked, you plural walked, they walked, we walked. It's all the same word, just slightly different endings. English, you get extra words, and that's just confusing. So you can use that. That's a graph problem as well. There are actually things called Markov chains, which are chains. So more on the linked list side, but they are graphs that indicate the probability that something will follow something else. So they're directed graphs with weighted edges. How did I get off on that tangent? What was I talking about?
I think you said verse 5 instead of
Yeah, that still doesn't help me. Oh, right. Edge matrix. So that is efficient for looking up whether edge exists, efficient for traversing a graph, and you don't have to deal with losing reference to pointers and other objects. You have one array that stores all your vertices, and that's good, that's easy to deal with. And you have one multi-dimensional array that keeps track of all possible edges and whether or not they exist. Of course, if you have a lot of falses in that array, you are storing this massive multi-dimensional array that's storing absolutely no information at all. So that's where the term sparse comes from. A sparse matrix or a sparse array is one where most of the most of the values are 0, or in this case, false. So if you have end up with a sparse matrix, you might as well represent it in the linked list style. Questions? What time is it? 2:36. Let's implement one of these. So, lights. What? Graph. No, private. I'm not going to genericize this just for the sake of time. Let's say our values are no. That would be too easy. Let's do strings. Let's call this words. And let's say rather than booleans, we will use ints as our edge matrix. So basically, these are weighted edges. And public graph int size. So we'll specify some initial size. Words equals new string size. And edges equals new int size. Right? So far so good. We have the data for a graph. Let's create a main method. Let's we need to specify a size. Let's say 10. And let's implement a set method. And all this will do is, come on, words idx equals word. So this is not only not a generic graph, but This is a graph implemented to do a very specific thing. And that specific thing is something I made up on the spot, so we'll see how well it actually works. This could end up generate some pretty funny phrases. We should also implement a connect method. And we'll say this is a directed graph because while the sentence he went makes sense, the sentence went he does not. So we want to maintain this order. So index 1 is where we're starting from, and index 2 is where we're going to. And we should actually use ints. So this will be the probability from 0 to 100. Let's say. We're defining these things arbitrarily. So edges IDX1 to IDX2 equals probability. So our methods here aren't really doing anything all that complicated. Phrase gen set 0 Bob went to the store and he bought some cabbage. So that is a complete sentence. That is 10 words long. So let's figure out what our connections are going to be. So phrase gen dot connect. So I guess we should change these indices. So Bob can obviously be followed by went, and let's say 50% chance. What else can Bob be followed by? Bob 2? No. Bob the? No. Bob store? Bob end? Bob end would work. What is that? 5? And that's probably a lower probability. What's next? Bob he, Bob bought. Bob bought works. 7. Let's keep it at 50%. Bob some, Bob cabbage. Okay. What about went? What can went be followed by? Went Bob, went to, went the, went store, went end works. Put that at 20. Let's see. Went he, went bought, went some, Went some might work. I'll change these probabilities around. Went cabbage, no. That sort of thing gets really weird when you have something like, you might have postal service, but went postal is also valid. To translate that, crazy cabbage is a valid phrase, but went crazy is also valid. Went crazy cabbage, on the other hand, is not. All right, to Bob works. So 0, we'll leave that at 50% probability. And to the is probably the only one that works. What's next? The Bob? No. The store and the cabbage. So 4 and 9. What can store be followed by? Yeah. Let's add that in because that will break all sorts of ways. It can obviously be followed by and. Let's make sure I didn't follow 1 by 2. I might want to do that. 0 by 1, 1 by 2, 2 by 3, 4 by... I have to put at least what I have in the original sentence there. So follow 4 by 5. So what was I doing here? Store can be followed by the, right? So no, that's the one I just did. Store the, store and. I think that's it. Store some works. And Bob works. What are we on? 5? And Bob. And went works. Let me change some of these. So this is 3 was the, and store and cabbage. Yeah, that works. Yeah. For now, I'll just leave all of them at probability 50. And cabbage, and nouns. And went, and the. Let's do and the. And we'll put and cabbage in there. And now I won't be exhaustive. We just need some to stick in here. I guess I need 5, 6 to maintain the original sentence. So the original sentence is possible. He. obviously 7. He went. That's about it. Bought some, bought cabbage. And bought the. Let's see. Now some. Obviously cabbage. And I think that's about it. And we'll say cabbage and. Yeah, we'll say cabbage and. No, what was and? 5. Okay, so now we have we set up our vertices, we set up our edges. Phrase gen dot generate phrase. All right. Now let's have some fun here. Okay, so what we're going to do is generate a phrase that is 10 words long and see if we can make it make sense. So, string builder. String builder. SB equals new string builder. Initial capacity of, let's say, 200. No, 100. I don't think I have any words longer than 10 characters in there. So, for int I equals 0, I is less than 10, I plus plus. So, let's say int idx equals. Anyone remember offhand how maths.random works? I don't either. Random. Returns a double value with a positive sign greater than or equal to 0 and less than 1. Okay. That will work well. Math.random times 10 and cast that to an int. That will mean we get a number 0 through 9, right? Because it'll truncate, it'll take off that last part. So we will do sb.append words idx. Now we have to figure out where to go next, what the next word should be. Where to go next. So how do we find out where we can go next? So we have this edge matrix, and most of the values are 0. Where are the values non-zero? Dion. Where are the values in my edge matrix non-zero? Even though I'm typing, the question is still out there, so you can answer it. The code that I'm writing won't answer that question. Actually, now it might. So where are the values in my edge matrix not 0? This really has nothing to do with our application of graphs. This really has to do with how you represent a graph using edge matrices. having a non-zero value in an edge matrix is essentially the same as having a true value in a Boolean edge matrix. What does that mean? Yes. So, who wants to tell me what this method should do, assuming I wrote it correctly? Okay. Ideas?
So we can start the string of all the different relations in
Right. So the really interesting thing is how I do where to go next. And this is actually the simplest possible way. I want to traverse the graph. So which edge am I picking right now? Remembering that edges is my edge matrix, and edges subscript IDX is the edges that vertex IDX. So in this case, it starts out at, well, we don't set it. So the edges that vertex IDX are connected to. So if that's an array, its length is the same as the length of the array of vertices of words. So which vertex am I choosing? I obviously have to choose a vertex that this vertex connects to, which is why I'm testing for if the value in the array is greater than 0. If it's 0, it's not connected. I don't want to choose that word. What's unique about the way I'm choosing that word? And cabbage, 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 cabbage. Huh. Oh. Hang on. What did I do? IDX equals K. What can cabbage connect to? Cabbage can only connect to 5. So why is cabbage connecting to 9? This is called debugging. And I guess I should actually... What was and? And is 5. So, just to force it to start there all the time, so we can test this. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 5, 6. My only guess is that this continue is not being respected because it's ambiguous. That looks a little bit better. And Bob went to Bob, went to Bob, went to. Okay. That makes for some slightly boring sentences. Let's comment out all this debugging stuff. And bring this back. And compile. Run. Cabbage and Bob went to Bob, went to Bob, went. To Bob went to Bob, went to Bob, went to. The store, the store, the store, the store.
This is the greatest thing ever.
Isn't it? I have to do something fun on the last day of class. Bob went to Bob, went to Bob, went to Bob. If we had Buffalo in there, we could do Buffalo, 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 which is apparently a valid sentence. Any number of Buffalo next to each other is a valid sentence, which is scary. And we get a lot of Bob went to Bob, went to Bob. So let's fix that. So rather than simply picking so this is the answer to that question. I am picking the first one in the list that has a non-zero edge weight, which will always make for boring sentences. So instead of doing that, let's this is going to look a lot like we can get rid of this. A lot like a search for a maximum value or something. So we will have int max argmax. And we're not just going to pick the greatest probability, because this is probability. We want some randomness in there. So we'll use this math.random as well. So here's probability. And we'll actually multiply that by math.random, and cast all that to an int. Right. And then if probability is greater than max, we'll start like that. Probability is greater than max, then we don't set IDX to k, we set argmax to k, and we set max to prob. So this is a probability max search. So the thing with the greatest probability has the greatest probability of being chosen, but it won't necessarily get chosen. At the end, once we figure out what has actually gotten the maximum, that outside the for loop. So IDX equals argmax. So this is both graph traversal and graph traversal with some sort of probability of which path we're choosing. So it's not depth first search, it's not breadth first search, it's probability search. This is very similar to what happens with Markov chains. So let's compile and get rid of go. To the store the cabbage and Bob bought. A little saner. Bob went to Bob, bought the cabbage, and he went. Cabbage and he bought some cabbage and went to Bob. Bought some cabbage and went, went to the cabbage and went. He went to Bob, bought some cabbage. He went to the cabbage and went to the cabbage. Bob went to the cabbage and he bought the store. Now, if you have, the idea behind something like that is that you train this on a very large corpus of text. So you take actual text that people have actually written, and you take, we have two things here. We have the vertices and we have the edge weights. The vertices are the set of all words in this corpus, everything that anyone has ever said in this piece of text. The probabilities are computed by taking all occurrences of, say, the word cabbage, and taking all words that happen after the word cabbage. Computing how many times the word cabbage is followed by some word. Let's say that's 14. And if it's followed by and 3 of those 14 times, you take 3 divided by 14, and you get some probability. And that... Cleverbot is based off something like this, yes. There are... This is kind of the very simplest that something like that would be based off of. There are other heuristics, like we didn't have any data in there. We could have stored something with each vertex indicating whether it's a good beginning of a sentence word. We don't have anything saying this is a good end of sentence word, and then we could have some probability of deciding if we're at an end of sentence word, do we end the sentence here or do we continue? And that probability could also be weighted by how many words we've added to the sentence overall. So there are a bunch of different things you can do to improve the sanity of the phrasing. It certainly makes it funnier.
I had a buddy of mine had fun reading in high school, and talked about the middle of the board, and then afterwards, the middle girl, some people stare at us and long
Yep. Is anyone familiar with IRC? It's a little outdated. Okay, it's not outdated at all. Getting involved in an IRC channel is probably the worst thing you can do for your productivity ever. When I was an undergraduate, all of 5 years ago, I got involved with an IRC channel that was started at Lehigh University. And we have a bot that does something like this. If you're bored, you just prompt it to say something. And it actually, not only does it's closer to the Cleverbot end of this spectrum, not only does it create a random phrase, but it takes the words that you have sent to it and tries to work them in there somehow. So the words that you started with have a higher probability of appearing in what it regurgitates. Not in the same order, not in the same context, and you get some pretty crazy things going on. Alright, any questions about graphs? Do you all feel prepared for the final? Cool. So that's it for today, and that's it for the class. We're done. Exam Thursday.